Hi everyone, I'm Pierre Soupli and I'm working at the EPITA's System and Security Laboratory, okay, which is called LSE. And today I will talk about my travel about understanding how pinball works. Okay, first of all, this is not a serious talk, okay? This is only a hobby. I'm not presenting an academic work, okay? This is only a hobby, okay? And don't judge me, please. Okay. Let's talk about my pinball. This is a Sega Whitestar Pinball, yeah, because Sega actually did pinball. And it was, in fact, released in the late 19th. And this is my pinball. This is actually a Starship Troopers pinball released in 1997, yeah, which is really recent pinball, yeah, and it's a really cool pinball. Okay, in fact, as you may know, on a pinball you have a lot of actuators, of coils, in fact, to interact with a play field and etc. So to control all this actuator, you have an I/O board. This I/O board is controlling the 50-volt power supply, which activates all the actuator. Okay, and this I/O board is controlled by a CPU and a soundboard. Okay, on this board you have all the software which control all the pinball. Okay, in the same board you have in red here the main CPU. Okay, which supervise the whole game. Okay, and in blue you have the soundboard. Okay, so just let's talk a little bit about the main CPU. This is not the real purpose of this talk, but let's see how it works. This is basically a Motorola CPU, okay, which is pretty old today, but back in the day it was pretty CPU. And the address decoding was based on which is called a PAL. Okay, a PAL is in fact a chip in which you can program a logical address, a logical expression. Sorry. So in fact, you have on input you have your address bus, and then according to the value that the CPU puts on the address bus, it just activates the corresponding device. I mean, here you can select the ROM, the RAM, or all the I/O, all I/O. Okay. In fact, this is a one-time programming. I mean, the manufacturer just takes the chip and program the chip, and this is done. Okay, you cannot reprogram it. The idea here is to get the logical expression which are coded inside this chip. This can be done by simply testing all the inputs and then dumping the truth tables from it. Okay, and when you've got your truth table, here I'm doing it with a simple Arduino. Okay, and afterwards, you can simplify your truth table, which can take a lot of time, okay? And then you can find the logical expression associated to the outputs, okay? And when you've got it, you can define exactly the address space of the CPU. Okay, after that, I was able to say, okay, the address space has this layout, okay? But in order to test it, I wanted to create my own firmware, okay? And the firmware is contained on a new EEPROM, okay? And you can basically replace it by a more recent flash memory, which is basically the same, but you just have a pinout mismatch. This is not really important here, but you can create your own firmware on this kind of flash. Okay, here is my custom flash programmer, because I didn't have any flash programmer at the time, and I just created it with an Arduino Mega. Okay, and with it, I was able to write the name of my laboratory on the LCD display. Okay, that's how the main CPU works. But the purpose of this talk is the soundboard. Okay, the soundboard is horrible. In fact, the sound that is output by this pinball is really noisy, and we can suppose that it is a quite simple board. Not at all. Okay, let's talk about, let's see how the soundboard looks like. You have first another CPU, which is exactly the same as the main CPU, and which is dedicated to interfacing the main CPU to a custom DSP. And the custom DSP is here, and it's, this is a really strange DSP. This is a custom DSP which is called the BSMT2000, and this is a DSP that you can find on many arcade machines. Okay, it's a proprietary chip. I mean, you don't have the datasheet of this chip, and you can find here some EEPROM which contains the samples which can be played by the board. And here you have some filters and amplifier in order to amplify the analog signal outputted by the DAC converter. And then you can wire here, you can connect the speaker here. Okay? That's pretty simple. So, as I said, you have your main CPU. You have the sound CPU, which is connected with the main CPU. Yeah. So the main CPU can send commands to the sound CPU, and the sound CPU translates it to the DSP. Okay? That's pretty simple. So you have exactly 3 buses in this board. Okay. In fact, as you can see, the DSP is directly connected to the voice ROM, which contains all the samples as I described just before. And this is basically samples which are encoded using PCM, which is 8-bit PCM at a rate of 8 kilohertz, which is the same rate as the phone. Okay, and here in this ROM, you just find all the samples that are played by the pinball. Okay, all, but you cannot find exactly the background sound in this ROM. You just have only sound like explosion, voices, etc. But you do not find any melody in this ROM. So the question is, where are the melody? Okay, let's focus on the sound CPU. As the main CPU, the address decoding is based on a PAL, okay? And let's see how the address space works. We can apply exactly the same technique that the main CPU, so you can dump the content of this PAL, and then you can find that the address space looks like that. You basically have on the bottom of the address space the RAM, and then you've got some I/O, and then you have on the higher address, you have different address space according to the operations that you are doing. If you are reading, you just read on the ROM which contains the code, okay? And if you write, you can directly talk to the DSP. This is in fact due to the very restricted address space, which is a particularity of the Motorola CPU. Okay, you have only a 16-bit address bus, which is really restrained. So they use this technique to overlap, in fact, these two devices. Okay. You have got, just about the wiring, you have a kind of status register which is used to reset the DSP and just to indicate to the main CPU that the audio board, that the soundboard is ready to accept a command. Okay, let's look at the interface between the main CPU and the sound CPU. This is actually quite simple. The main CPU can only send an 8-bit word to the sound CPU. This is really short. And in fact, the command is located on a register, which is dedicated to that. And on the input are connected to the data bus of the main CPU, and the output is connected to the data bus of the sound CPU. And this is the interface between these two CPU. Okay, let's take an example. And let's imagine that the CPU wants to send a command, okay? So it's basically done by loading first the command on the age register and then store it on a specific address which will activate the sound strobe signal. Okay? Then it will activate the register, and then the command will be loaded on the register. It's really simple. The only thing is, when you use the sound strobe signal, it will activate this D flip-flop, and it will indicate to the sound CPU that the buffer is full with a dedicated signal. Okay? You've got here an FRQ signal. This is here connected directly to the clock signal. So it means that periodically the sound CPU receives an FRQ. And when it basically receives this kind of IRQ, the sound CPU is simply reading on this register, and it will get the command. If a read operation is done here, it basically resets this flip-flop, and then the buffer full is disasserted. That's really simple. Okay. Basically, on the FRQ handler, so as I said before, it just pulls the value, and it will just push the value on the specific ring buffer, nothing special here. On the main loop, so I mean not on the FRQ handler, the sound CPU is basically dequeuing the commands, and then it uses a kind of descriptor for each command, okay, which are located on an array, okay, and the command that the main CPU sent to the sound CPU is in fact an index to this array. This structure is basically really hard to understand at this point, because in fact you can basically know that the first field is used to as an index on a jump table, okay, which is the handler of the command, and the offers are not really clear at that point. You can find that this field can be basically a mask, and then you have got a pointer to datas, but you can know what it is. In order to understand how the firmware works, it could be a good idea to try to understand how the DSP can be controlled. So let's look at the DSP. Okay. The interface between the sound CPU and the DSP is quite more difficult, or quite more complicated by, compared to the main CPU to the sound CPU interface. This is actually done by 3 registers, okay? A command is composed of 2 words. You have a 16-bit words which contains the data, and you've got an 8-bit word which contains an address, okay? And with those registers, you just latch the value like that. First of all, the sound CPU loads the most significant byte of the data, okay? It loads it on the first register, okay? Nothing special here. And then it will load the second, the least significant byte of the data on the second register. And by doing it, in fact, the address is latched on the third register. So you've got a base address, which in fact defines a range in which if you read or write on this area, you will select this register. So the offset from this base will be stored on the third register, okay? And this is exactly what defines the address of the command, okay? That's a little bit tricky, but it works. Okay. Now, the DSP can read the command by simply reading the address, okay? And if the address is different from 0xFF, it means that it's a valid address. And if the address is valid, it can then read the 16-bit data word, okay? That's pretty simple. And in fact, you have got an extra feature which, in fact, trigger an IRQ to the sound CPU. But in fact, according to the firmware, I don't think it uses actually the IRQ signal, but it only use the B-load signal, which means that the buffer is full or not. Okay. Now let's talk about the DSP to the DAC interface. Just quickly. The DAC that is used, which is a digital to analog converter, is one of the first DAC that uses the I2S protocol. The I2S protocol is nowadays pretty common. It's basically a protocol made to transfer audio stream between two integrated circuits. Nowadays, it's pretty common, but at the time, it was one of the first chips which handles this protocol. And it explains why you have a lot of glue logic that converts the parallel data to the serial protocol, which is the I2S. Okay? So nowadays, in fact, all this glue logic can be found in a single chip today. Okay, let's focus on the BSMT2000. This is, in fact, if you look at the internet, you will find that this chip is actually a mass-chrom version of a TMS DSP. The TMS DSP is basically a DSP made by Texas Instruments, which is one of the first DSP made, and it was a pretty old version of the TMS because it still exists today, but here it's a really old version. Basically, this supposition can be right because, in fact, the pinout of the BSMT2000 is exactly the same that this DSP. So we can suppose that yes, it's a TMS. Yes, it's a TMS DSP. Okay, here is a block diagram. Not really important. Just to know, it's a DSP. So basically, it's a CPU that can only do multiplication. This is basically that. That's a really strange architecture, in my opinion, because you have only one register, which is an accumulator, and all other registers that you can use can only be used to make to be different from to be used to access to address the data memory. That's pretty strange. That's DSP, and that's really powerful if you want to make digital signal processing. Okay, basically you have one pin which is really useful on this kind of DSP. This is the MC pin. This pin, in fact, defines if you want to use the DSP as a microcontroller or a microprocessor. If you use it as a microcontroller, the instruction will be basically fetched from the internal program ROM, okay? But if you use it in microprocessor mode, it will fetch its instruction from an external memory, okay? So let's try to use this pin on the BSMT2000. And in fact, if I configure it as a microprocessor mode, yes, the BSMT is actually trying to fetch instruction from an external memory. So bingo, we can try to inject instruction to this DSP. This pin is actually designed to be hardwired. I mean, when you design a board which is based on this DSP, you have to connect this pin to 5 volts or ground according to the mode that you want to use. But when you are using this DSP, you are not supposed, in fact, to change its value. Okay, you are not supposed to change the mode while the DSP is running. So what happens if we try? Okay, there is an instruction which is pretty useful. This is the TBLR instruction, which is dedicated to read from the program memory and then put the value read directly on the data memory, okay? And then we can use the out instruction. We can read on the data memory and then output the value on the external bus, okay? So what happened if I basically change the value just after, the TBLR instruction? Let's try, okay? So let's try with this basic chronogram. You can find here the address bus, okay, and the data bus, okay? So basically, if I configure the DSP in a microprocessor mode, it will try to fetch an instruction. So yes, let's drive the TBLR instruction, okay? And then we assert this pin, which changes the mode of the DSP. In fact, you have a little prefetch queue, which means that it will try to fetch the next instruction. So let's feed the next instruction. And then you will see that it will try to compute here. It will try to read in its internal memory, okay? And then it will basically latch the value read from the mask ROM directly on the external bus. In fact, the value that I get here was a valid instruction, a valid TMS instruction, which means that it was directly data that was from the mask ROM. So yeah, with this technique, we can basically read on the mask ROM. Okay, how can we achieve now to read the entire memory? Actually, I used an FPGA to do that. I just program a little bus controller in Verilog, and I used two internal memories. Internal memory, which represent the program memory of the DSP. So in fact, I can put codes in that. And in the second one, this is in fact the copy of the mask ROM contained on the DSP. Okay? So basically, the bus controller just see if the opcode of the TBLR instruction is latched, and then if this instruction is driven, it just basically reads the next word and put it on the shadow mask ROM. Okay? So the program that I have to put on the external program memory is something like that, basically a loop which basically reads the entire memory. And with that techniques, I can read and dump the entire memory of this DSP. So this is my test bench, which is actually here. You can see the BSMT2000, some resistor here because this is a chip which is dedicated to, which is driven at 5 volts. But here my FPGA, it's 3.3 volts. So I have to interface with some resistor to limit current. And then I use an FPGA board, which is an Altera Cyclone 4. So now we have got dump the firmware. So let's try to understand how it works. First of all, the address space of the BSMT2000 is quite simple. It can basically read the data coming from the sound CPU. Yeah. Okay. So and you've got the output when you can basically latch EEPROM address and left and send samples to the speakers. Okay, here is the code which is used to initialize the BSMT. Not really important. Up, and then you've got that the BSMT is basically doing this code in its main loop. Okay, and it's basically mixing the signals from 12 different channels. Okay, you've got a special channels here, which is a kind of AD PCM, but I don't think it's used in this pinball, and you can only find PCM streams on the voices ROM. So I suppose that the last channel is not used. Okay, the second step on the main loop is basically read the data from the sound CPU. Okay, so basically it reads the address that has been latched, and then it reads the data and basically write on the address indicated by the sound CPU. It basically means that the sound CPU can write anywhere on the memory on the BSMT2000. So is there any trouble by doing it? Not really, because in fact it uses some ranges which are predefined. And in fact, it writes on other range. It does not make any problem because in fact it never reads in other part of the data memory. Okay, so now that we understand how the DSP works, let's go back to the sound CPU firmware. Okay, so basically you can basically find how the DSP is controlled, okay, by those subroutines, okay, and by reversing it, you can then find the other functionalities of the sound CPU. So basically, if we take exactly the structure of a CPU command, we can find that this pointer points to an array which contains, in fact, addresses of some bytecodes. Okay, and those bytecodes is, in fact, the bytecode which represent an audio pattern. Okay, so basically, if you want to just play a single sample, okay, you just use a simple instruction, which means, for example, here 05, which means load a PCM sample, and then you set the channel volume, you set the channel rate, and then you wait until the sample has been played. Okay, this is basically a kind of virtual machine contained on the sound CPU. Afterwards, you can find that all PCM samples are described on an array, and then you can segment the voices from this array, which is really simple. And then you can find that two samples are used really often. I mean, those two samples are often in almost all patterns, and in fact, they are used to create a note. And in fact, the melodies is basically generated by this bytecode, okay, by playing this sample at a different rate in order to create a specific note, okay? Okay, basically the track, each track is represented by a structure, okay, which is arranged in the in-place linked, double-linked list, okay, nothing special. You just have an instruction pointer, the counter, okay, and you have a type, which means, which represents, in fact, the type of the song that is played, that is currently playing. In fact, you have the 0, okay, which represents a background track, and a 1, which represents a sound track. Okay, basically, you have several channels with a different track. Okay, basically, you have the background track, which is run on each channels, and then when you've got a specific song, it just use a specific channel, okay, and it just mute the original background track. Okay, nothing special here, but it's basically something really, really smart. In fact, you have a board which is not a really good hardware, and in fact, you can see that the firmware on the sound CPU is using, in fact, this design in a really good way. This is actually a really good state-of-the-art design for a sound chip, but it was really good. It was a really good design in the 80s. However, this pinball was released in 1997, so which is maybe a little bit of a part of the pinball folks. So, thank you very much.
Thank you very much, Pierre. We have time for 1 or 2 questions. Yes?
I was just wondering, where do you obtain the specifications of the board itself? Is it
you do not have the specification of the board. Yeah. This, in fact, it was I reversed the PCB by myself.
Other question, comments? I have one. How did you decide to study this pinball and not?
Because I have one first. But yeah, in fact, that's a pinball which is a good representative of a second generation of pinball, and in fact, it's pretty interesting, in fact, to reverse this kind of pinball, because this is not too simple, but this is not the kind of pinball that you can find today, which are really complicated.
Other questions? Comments? Okay, I hope you have sent some rump talk to the organizer. Still have some time, and we have a half an hour break. We resume at 4:15. Have a nice break.
Thanks.